Alright, we're going to take a look at vector and scalar quantities. This is not a full treatment of the subject. This is just what you need to know to do problems in AP Physics. But if you'd like to know more about it, you can ask me or any of the math teachers at the school. Alright, so let's start with some definitions. The first thing to know is this. Scalars and vectors are both quantities. They are just things that can be measured, but they're different in as much as they have to be represented by different amounts of information. Let me show you what I mean. A scalar is anything that you can fully represent or give all the information about it just by giving its magnitude. And the word magnitude, by the way, that means size or amount or largeness or smallness. It's just like how big or how much. So an example of a scalar would be something like, hey, how many cars are parked on your street? You could go outside, you could count the number of cars, and then the answer would be the same no matter what direction you counted in. I mean, you can't count the number of cars in a different way where you get the right answer. You could count in many ways where you get the wrong answer, but I assume we're all competent counters. Vectors are very different because you can't give a vector quantity with only its size or what we call magnitude. You have to give its direction as well. And the reason for that is hopefully going to be apparent after we look at two examples. The first is this. Frequently, we use words that really are directional words, especially the words up and down, even though we're not talking about direction at all. We're really just talking about changes in size, or again, we call that magnitude. Here's two examples. If I say, hey, what's the temperature in this classroom? You might look at the thermostat and you say, oh, it's 70 degrees Fahrenheit. And then I could say, boy, it sure is hot in here. I'm going to turn the temperature down. Or conversely, I will turn the temperature up because it's so cold in here. So we use these words up and down even though temperature doesn't have a direction. So if I say, oh, the temperature has gone up, that doesn't mean that the temperature that was already here has vertically ascended into the sky. That's not what we mean by up in that context. Same thing is true of mass. If I ask you, what is your mass? You know, how much do you weigh? People frequently talk about their weight in terms of going up and going down. My weight has gone down. You know, I've been on this diet and I've been running. But up and down, once again, don't mean direction. They just mean size. If my weight goes up, I've just gained more mass. I haven't gone vertically upward. It's not directional. So up and down especially can mean magnitude or direction. So we have to be very careful about the language we choose when describing scalars and vectors. All right, let's try an example so you better understand scalars. This is straight out of first grade, so go ahead and pause the video and grab some pencil and paper if you need to. Just resume, whenever you think you know it. Here's the great thing about scalars. You already have all the information you need. It's not a trick question. The answer is 5, and that's it. And the reason that it's important to know that scalars work this way is because all the numbers you learned in primary school were scalar quantities. You know, if you have 3 and I give you 5, you have 8. If you have 10 and I take 6, you have 4 remaining. I mean, those are scalar quantities. It doesn't matter how you do it. Those are just the answers independent of direction. Let's try a different example. Let's say you drive 3 miles and then you drive 4 more miles. Now here's where it becomes kind of interesting. How far are you from home? You might be tempted to say, well, I must be 7 miles from home. You know, I drove 3 and then I drove 4. But now I hope you start to recognize why direction is a very important part of the definition of a vector. You can't answer this. You don't have enough information because you need to know which directions you were driving. If I drive 3 miles north and then 4 miles south, I'm only 1 mile from home. But if I drive 3 miles in one direction and then 4 miles perpendicular, like 3 miles north and then 4 miles west, I'm a different distance from home. If I drive 7 miles in this fashion, 3 miles east, imagine you're looking down at a map here such that a compass rose could be superimposed on the screen, but I'm lazy and I'm not going to put one on there. Up is north and right is east. 3 miles and then I drive 4 miles east again. So how far am I from home? I think this one's pretty apparent. You're 7 miles from home. This is a good time to introduce some new language. The 7-mile vector, or this arrow that I have drawn, you'll notice that it doesn't only have the number 7, which is the sum of 3 and 4, and that makes sense. It also is exactly the same length as the beginning of the 3 to the end of the 4. See how those match up? And that's important because that's actually how you add vectors. We call this single vector, this single arrow that starts at the beginning of the first and ends at the end of the second, or really it ends at the end of the last vector. There just happens to be 2 in this example. We call that the resultant. The resultant is the sum of all of the vectors. So we also have two terms to describe the beginning and end of vectors, because that can be confusing. We call the end with no arrow the tail, and we call the end with an arrow the tip. And so every vector has a tail and a tip. So the tail is already marked on this 3-mile vector. Its tip is here. I haven't marked it, but it's where the arrowhead is. And then the tail of the 4 vector, you'll see here, starts at the tip of the 3. And that is really, really important, because whenever you need to add vectors, we always do it in this fashion. We put the tail of the next vector at the tip of the previous vector. That term resultant I mentioned, by the way, that means, definitionally, it means the vector that is drawn from the tail, or the beginning, of the first vector to the tip of the last vector. So here, like I said, it was the beginning of the first to the end of the second, but that's only coincidence that there happen to be 2 vectors and that they happen to go in the same direction. I mean, we could have put these arrows in any direction and had any number of arrows, but the answer for resultant is the same. You start at the beginning of arrow 1 and you end at the end of arrow last, whatever the last arrow is.